Welcome back. In this lab, we're going to step inside the network and follow a packet as it travels across multiple routers. Our topology consists of 3 routers and 3 networks connected together. The mission is simple: send a packet from PC1 all the way to PC3 and observe how the network delivers it. Along the way, we'll watch how routers make forwarding decisions while MAC addresses change at every hop, while the IP address remains the same. Before we send any traffic across the network, let's take a quick look at how the network itself is structured. In this lab, we have 3 different local networks connected by 3 routers. PC1 sits in the 192.168.1.0/24 network and uses R1 as its default gateway. PC2 is located in the 192.168.2.0/24 network and communicates through router R2. And PC3 sits in the 192.168.3.0/24 network, which is connected to router R3. Now the router themselves are connected using smaller point-to-point networks. R1 and R2 communicate over the 10.0.0.0/30 network, while R2 and R3 communicate over the 10.0.0.4/30 network. Each router interface represents a different network, and routers exist to move packets between these networks. Now that the addressing is in place, the routers still need instructions on how to reach networks that are not directly connected. In the next step, we'll configure static routes to tell the network exactly where packets should go. Routers automatically know about networks that are connected to their own interfaces, but they need additional instructions to reach remote networks. In this lab, we accomplish that using static routes. Static routes allows us to manually tell a router where a specific network exists and which next hop should be used to reach it. For example, router 1 needs to reach the 192.168.3.0 network, but that network exists behind router 3. So we configure a static route on router 1 pointing to router 2 as the next hop. R2 then forwards that traffic towards R3, which ultimately delivers the packet to the correct network. Once these routes are in place, the router now have a complete map of how to reach each network in the topology. Now that the routers know how to reach each network, we can test connectivity across the topology. From PC1, we'll send a packet to PC3 using a ping. This allows us to verify that the packet can successfully travel across multiple routers and reach the destination network. The replies we receive confirm that the packet made the full journey from PC1 across router 1, router 2, and router 3 before reaching PC3 and returning back. As we can see, the packet first reaches router 1, then router 2, then router 3, before finally arriving at PC3. Now that we've seen the path the packet takes across the network, let's take it one step deeper and observe what actually happens to the packet at each hop. The first thing we see is an ARP request. Before PC1 can send traffic outside its network, it must first discover the MAC address of its default gateway. So PC1 broadcasts a message asking who has 192.168.1.1. Router 1 replies with its MAC address. Here we can see the ICMP echo request leaving router 1 towards router 2. Notice that the source IP is still 192.168.1.2 and the destination IP is 192.168.3.2. These addresses do not change because layer 3 communication is end-to-end. However, we can see that the time to live has decreased from 64 to 63. This happens because every router decrements the time to live before forwarding the packet. When the packet reaches router 2 and is forwarded again, the time to live decreases once more. Now the time to live value is 62. This shows us that the packet has passed through another router. Even though the IP addresses stay the same, the Ethernet frame is rebuilt at every hop. Each router removes the old layer 2 header and creates a new one addressed to the next device in the path. Now the packet finally arrives at router 3, which is directly connected to PC3's network. We observe an ARP request coming from PC3 asking who has 192.168.3.1. This is PC3 discovering the MAC address of its default gateway so it can send a reply back toward the source. This shows us that communication in the network is bidirectional. While one device is receiving data, it is also preparing to respond. This lab highlights one of the most important ideas in networking. IP addresses identify the final destination of a packet, but MAC addresses identify the next hop. As the packet moves across the network, routers repeatedly remove and rebuild the Ethernet frame while forwarding the packet closer to its destination. By capturing the traffic at each hop using Wireshark, we can actually watch the network make these decisions step by step. And when we begin to observe networking at this level, we stop memorizing commands and start understanding how the network really works.